So good afternoon all of you, and sorry for that delay. So I'll touch upon the frequency selective surfaces and its applications. The plan is like to introduce what is FSS for the first 10 to 20 minutes of time, and then I'll discuss about what are the things what we completed or did using this FSS, and what are the things we have published, and the explorations and research what we have done in this domain, particularly FSS. And then I'll move on to what are the potential applications and the way beyond, like the current trends, for example, the window based antennas for 5G and 6G communications. Okay. So to start with an FSS, yeah, before that, how many of you are working with this FSS here, or anyone aware of FSS? Okay, thank you. So FSS is like frequency selective surface. It provides a frequency discrimination. It means it either transmits or it will stop. The other case, I can absorb it as well. Okay, how we are going to do that? Again, by making it's a two-dimensional periodic array element based on the unit cell. Each and every element in that two-dimensional array can be called as a unit cell. So that unit cell we have to engineer so that we can make it as a band pass or a band stop, or we can absorb the incident electromagnetic signal of our interest. For example, if you want to design a filter, which is spatial filter, which is band stop, then we need to have a metallic patch that forms the fundamental block of this FSS, that is the unit cell. If the unit cell is in the slot mode or a slot type, then that will act as a band pass filter. Okay. So what are all the so if we have a patch, so it is replicated along x and y axis. So we have an array of this kind. So we call it as crisscross patch. So for which each and every unit cell is a patch kind of thing. So that will give us a transmission response like this. So this patch gives us a band stop response at one particular frequency. And if it is a slot, the complementary of this gives us a band pass response. So how to realize a absorber? So when we check only the insertion loss S12, so we call it as a band stop filter. If I am also interested in the absorption capability of the filter, we need to check for the reflection coefficients as well. Okay. So can I go for only the crisscross structure? Not. We have so many other unit cells as well. These are some of the fundamentally used unit cells. For example, we have some 3 to 4 groups from which we can initiate the research activities with respect to this frequency selective surfaces. So we can go with either center connected or N poles, or we can go with loop types, or the solid types like a solid patch, or a square patch, or it can be a circular patch, or we can go for a combination of all these things. So it is not limited to only these four these four groups. We can also extend it to some other designs as well. So I will explore those things. So when we design, for those who are not aware of these frequency selective surfaces, when we want to design an FSS, we have to make sure that two characteristics are satisfied by the design what we go for. The first one is the polarization independent characteristics. So it is like for any electromagnetic incident, okay, it can be a vertically polarized or it can be a horizontally polarized. For that incident electromagnetic signal, we need to make sure that the designed FSS provides a stable response. How it is possible, how we can make it feasible with the help of the design? By making the geometry of the unit cell, like what we have seen in the previous slides. All the unit cell combinations, whatever I have discussed, everything is symmetrical in geometry. That is to cater for this polarization independent characterization. Next one is angular independency. For the incident electromagnetic signal, which is on this FSS surface, what we have designed to get band stopped or passed or to get absorbed, we need to make sure that should happen for all the any angle of incident, okay, of the electromagnetic waves. So we need to make sure that the unit cells whatever we are designed is of miniaturized in nature to satisfy this angular independency. So when we speak about angular independency, two things we need to consider. One is for different angles of theta as well as for pi. So what are the applications? So the fundamental applications are like band stop or band pass filters. Nowadays we are this FSS is used for electromagnetic shielding applications, antenna gain enhancement, chipless RFID tags, then polarization converters, intelligent reflecting services, and surface health monitoring. So when we speak about this electromagnetic shielding, so it is like reducing the electromagnetic field in a particular enclosure. For example, when we go for any antenna design, if I want to characterize it, we go for anechoic chamber. So actually a chamber is the best example where we can say it is shielded from the external environment, as well as the radiations within that chamber is not going to be released, or we could say that is going to disturb the external environment. So to realize that, we go for this kind of FSS. So the very typical electromagnetic shielding component was the Faraday's cage. So that blocks everything, but that's not the thing we require. So we want to have external connectivity as well. So we need to select a particular frequency for which I need to stop or pass or absorb. Oh, there are some applications that demands that. So it refers to enclosures used to isolate electrical devices from the surroundings. Okay. So how to measure this efficiency or the shield, capability of the device as an electromagnetic shielding component? So we have a figure of merit. We could say the shielding effectiveness. So shielding effectiveness, I can find it with the help of this formula, like 20 log the ratio of incident electromagnetic field to transmitted electromagnetic field. For example, our stainless steel tiffin box, what we have or we use regularly, will provide some 50 to 60 dB of attenuation, that is shielding. So if I have a proper shielding, in all the anechoic chambers will provide 80 to 90 dB of attenuation. If I say it is 100 dB of attenuation, 1 part in 1 lakh of the electromagnetic field is only allowed. So that is the impact of that electromagnetic shielding. So can we provide this amount of shielding with the help of this FSS? Yes, definitely, but we want to have some 2 to 3 layers of FSS, or we can go for 30 to 40 dB of attenuation with the help of single layer frequency relative surface. Next comes, definitely the next question will be, what is the material what I need to use? For example, those who are already working in this domain, they may be aware of the FR4, duroid, and even polythene. All these material can be used as substrate. For example, if I want to control the electric field alone, then I need to go for the conducting components. For example, along with the substrate material FR4, we need to go for some conductors. And if it is near field, so we have electric and magnetic field. If it is near field, it is electric field is predominant. Okay, and if it is the source is a loop, then we have near field where magnetic field is predominant. If it is a far field, we have plane wave. So based on the field, whether it is near field or far field, even in the near field, whether it is electric field or magnetic field, we need to choose the material appropriately. For example, if it is far field, we can go for conductors. It is not that a standalone conductor can provide the required electromagnetic shielding. Yes, it will, but for the desired bandwidth, we need to go for a sandwiched kind of frequency selective surface. So if it is near field, we go for, if it is predominantly electric, we go for conductors as the most preferred material, and if it is predominantly magnetic, we go for ferromagnetic materials. Okay, so based on these understandings, we have come up with some 3 to 4 different types of FSS for shielding applications. The first one is like miniaturized FSS for WLAN shielding, that is wireless LAN. So this is how the FSS structure or unit cell, I could say. So we need to replicate this along X and Y axis to provide the effective electromagnetic shielding at the frequency of our interest, since we chose the application being shielding WLAN. So we located it to be around 5.1 or 5.2 gigahertz. So all these colors, different colors, means angular stability as well as polarization stability. So here TE mode, TM mode, it conveys the FSS design satisfies polarization stability, and angles 0, 30, 60, it conveys that it satisfies the angular stability. So this is the measurement setup. and we did all these measurements at Samir in Chennai. And what are the features of this particular FSS? So the miniaturized FSS, which is to shield the 5.1 GHz WLAN signal, is of dimension 0.095 lambda cross 0.095. So at 20 dB reference level, we are able to provide 460 MHz of bandwidth. Now the recent papers, you could see even 1 GHz bandwidth is also possible. We have come up with such kind of FSS. Okay. So next, how to extend this for dual band or triple band? Suppose if we have two resonating lengths, so here it is L1 and L2. In the previous case, we have had only one resonating length. Since we have two resonating lengths, so we have two resonant frequencies corresponding to 2.54 and 3.54. So what decides this resonance? So again, depends upon the length. Okay. So L1 gives you lambda 1 by 4, and the F2 is decided by the length, which is L2. So whether the length alone contributes to this frequency selective surface property, definitely I can say not. We have a role played by the substrate thickness as well as the thickness of the material. Like if it is a conductor, that thickness also plays a very important role in deciding what should be the amount of attenuation provided by the designed FSS. So we have tested it for different angles as well as different modes of polarization. So when we design such kind of frequency selective surfaces to operate at two different bands, we may have a doubt whether this is stable or not, which suppose if we change the resonating lengths of L1 and N2, whether that is going to affect the other resonance. So we have tested that as well, and we have measured it. These are the measured results. And yeah, so this is a FSS made of a crisscross or crooked cross geometry, where we have reduced the miniaturization from 0.095 to 0.088 lambda, and this is resonating at 2.54 and 3.54. So this is for a static response. Suppose if you want to change the frequency, convert the FSS from static frequency response to dynamic, or we could say if you want to change the response or shielding component, then we can go for passive reconfigurable surfaces or simply reconfigurable frequency surface. So this can be active as well as passive. So we tried our hands with passive, but we weren't into active because that involved more of circuitry that is in turn adds complexity to the design. So we have tried out with this passive reconfigurable FSS. So this is the unit cell design, and this is the setup what we developed. So where if you change the spacings uniformly between the stacked unit cells, so we will be able to control the frequency response. So this is the response. For example, if the K, which is the distance, so this is the distance, this spacing between the arrays. Okay, so here we have columns. If it is changed from 10.5 to 15 and to 29, there is a change. We will be able to tune the frequency response. This is the frequency reconfigurable shielding surface, which covers three frequencies starting from Ymax, WLAN and ISM band. So this advantage what we claim is that we are not using varactor diodes or pin diodes, but whereas we can also design with the help of those circuitry, but that adds complexity. Okay. And that will also come with some kind of advantage, like we can bring in uniform level of attenuation. Here there is varying attenuation that can be overcome with the help of the diodes, or if we go with any other active components. Then this is three-dimensional FSS. So this provides an extra degree of freedom in controlling the frequency response. For example, this is a simple concentric cylinder where we have inner thread and outer thread, which makes the connectivity between the inner cylinder and the outer cylinder. If we change the height, effective height, that brings in turn the variation in the frequency response. Yeah. So when the effective height is changed from 15 to 22 and then to 25 or 28, we can have tuning, but not much wider tuning, but we can go for some fine tuning from 1.8 to some 2.5 or 2.6 GHz. So this is the fabricated prototype, and we have tested it as well. Okay. So the features are like we can tune the frequency selective surface to act as a shielding element from 1.86 to 3.10. So the polarizing independency is also possible because it is obviously it is symmetrical in nature and it is angular independent and provides angular independency up to 45 degree. And in some of the literatures have come up with this replaceable unit cells. Like we are aware of this some of the games where they were inspired from the 3D printing technology as well as some of the games where you could see I can replace it. Okay, whenever this conducting component or a conducting patch is being etched or placed onto the surface, it looks more of like a polyurethane foam, but it is not actually polyurethane foam. We have a structure like this. On this, we can have this kind of again polygon shaped conducting component. So that will change its shape based on the structure that provides the frequency selectivity. For example, this FSS structure consists of an array of cross dipole structures. It exhibits frequency blocking at 6.45 gigahertz. Okay, so here you could see if it is a 2D FSS, if it is flat, then the response is something different. Then if it is converted to 3D FSS, so it has a different response. So this is like they call it as replaceable FSS with the help of this replaceable unit cells. Then suppose if we think of like shielding the GSM signal within this auditorium, we may go for jammers or we can go for some kind of absorbers. So this we proposed like we can go for this FSS based on paper material as well as some copper strips, okay, without disturbing the ambience of as well as the aesthetic nature of the hall. We can bring in some kind of shielding. So we have in that pursuit we have designed this FSS flexible unit based on flexible unit cell. So that consists of two concentric square elements where we have some kind of convolutions. The reason why we go for convolution is that to accommodate low frequencies in a smaller unit cell. So the electrical length can be much higher, but we need to make sure that it is the physical length is much lesser so that we can make the FSS suitable for all angular incidence or angular independency. So this is the response what we got for this dual band FSS for GSM shielding, and this is the for varying angle of incidences the stability of the FSS is also studied. Okay, so this is the bending analysis and this is this fabricated one, and we have got some acceptable results for varying angles as well as varying polarization. Okay, so the next application, so far we dealt with the electromagnetic shielding. What are the applications? So we have chipless RFID tags. Instead of having the chip in the RFID, we can go for chipless RFID tags where you could see this squares. Okay, we have concentric squares. So each and every square, whether it is removed or if it is part of the design, the reflection coefficient is different. So based on the tags, we can design what should be the code that will be encoded. For example, if we have all the squares in place, that will have a code reflection coefficient which corresponds to all 5 ones. And if we remove a part of that, then we can use the same structure but with 2 or 3 squares loops removed that will correspond to code. So using this we can realize some RFID tags. So we call it as chipless RFID tags. Next, polarizer or polarization converter. So in the satellite communication we want to have the proper reception of the signal that is possible one and only if we receive the signal without any fading, or if there is any change in the orientation of the signal that is received, or change in the orientation of the polarization of the signal, okay, electric field. So this happens because of 2 to 3 reasons. One may be because of lower sensitivity to multipath fading or reduced sensitivity to Faraday's rotation, or it can be because of the rotation orientation of the receiver's antenna. So even in that case, if we want to receive that signal, we can go for this circularly polarized signal, circularly polarized waves. So if you have designed an antenna, if it is providing linearly polarized wave, so we can convert that into circularly polarized wave with the help of this frequency relative surface. So yeah, so this is a two-layer frequency relative surface. So they call it as cascaded FSS. The reason why it is cascaded is here is to provide a wide polarization converter. If you want to design a polarization converter for only one frequency, we can go for a single layer. In the frequency relative surface design, if you want to have a broad bandwidth of operation, so we need to go for clubbed layers of 2, 3 or even 4 layers. So this is the transmission coefficient. Okay, so this particular design provides the polarization conversion, that is from LP to CP as well as CP to LP in the 8 to 12 gigahertz band, so which covers this radar operations. So that is one application of a FSS in addition to what we have seen previously, that is electromagnetic shielding. The next application is this SHM, structural health monitoring. So when we speak about this SHM, it is not an invasive technique, it is a non-invasive technique where you have in this NDT, non-destructive technique, the sensors based on FSS have found application for this structural health monitoring. So for example, if you have a structure like this, if there is 2 degree, 3 degree bending, so if you have this FSS, then there will be a change in the signal received, or there will be some change in the angular response for that FSS. So with which we can check what is the angle to which the FSS has changed. Okay, so this is structural health monitoring, and I have one more example for that structural health monitoring. I'll discuss that. So this IRS is the one that is being researched nowadays. Okay, for 5G and beyond, we may make use of this FR2 bands. If that is the case, we may provide a larger bandwidth, but at the cost of path loss. So if we have path loss, how to overcome that? We need to go for more number of access points or base stations. If that is the case, then definitely that will add complexity to the system. So people have come up with this intelligent reflecting surfaces where these FSS, okay, are built or used to build this intelligent. So there is some intelligence behind this frequency relative surface. So whatever the signal is incident on this FSS, that will direct the beam, the incident electromagnetic beam, to the region of our interest by having some intelligence within it. So this is called as intelligent reflecting surfaces. You could see so many papers coming out with this IRS. So it is like when we go for this millimeter wave technology or the FR2 bands, so has the potential to overcome the poor propagation effects of this wireless channel. So yeah, this is the idea behind this IRS implementation. So we have the access point. Okay, we have IRS controller. This is the intelligent reflecting surface. I'll be able to change the beam of our interest. Instead of, suppose if we don't have this IRS, intelligent reflecting surface, whatever the signal that is incident on the wall will be absorbed, or it will be reflected. It may not be reflected in or to the region of our interest. Instead, if we want to reflect it without much attenuation, we can go for this IRS, that is intelligent reflecting surfaces. The next application is the antenna gain enhancements. So we want to have highly directed beam. For example, if we mount one antenna, for example, the one what we have in our mobile phones, okay, so it should receive the signal from the base station. Suppose if we mount it onto our mobile phone electronic with has this PCB and all those stuffs, definitely it will lose its OD nature, that is omnidirectional nature. If that is the case, definitely your gain will also get compromised. To overcome that, we go for antenna gain enhancing with the help of this FSS, where we have this antenna. Okay, this is the antenna, ultra wideband antenna. Beneath that we have this FSS. Okay, so this FSS in turn reflects the signal whatever is incident on it, and that will in turn add with the emitter electromagnetic wave in phase with each other, leading to constructive interference and finally enhancing the gain of the antenna. This is yet another application. Then the 5G, 6G, quantum has become the buzzwords, and there are papers in these 5G networks as well, like from 26 to 29 point gigahertz, can we design this FSS to enhance the gain of the antenna? Yes. So we have one example as well where the gain has been increased, okay, from 4.5 to 10.3, where they call it as some 5.3 dB dBi enhancement in the gain. So this is the antenna what they have proposed, and this is the FSS whatever is used beneath this antenna, and that helped enhance the gain. Okay, at 28 gigahertz they have enhanced gain of 5.3 dB, a big gain. Next application is the use of FSS as an absorber. Suppose if we could control the reflection as well as the transmission property of the FSS, then that can be converted to as an absorber. So the absorber range, the absorber is composed of 3 identical Teflon layers. So this is again a cascaded layer. This is the unit cell design. This will be replicated along X and Y axis to provide a wide band absorption capability. Here they claim it from 4 to 22 gigahertz of absorption, like some 10 dB of it is 90 dB absorption rate is there. Okay, this is using ultra wideband FSS for absorption functionality. Next is wireless passive sensors. So can I make use of this FSS for realizing some sensors? So in one paper they have dealt with this using this FSS sensor to check or to monitor the temperature of the object we are interested in. So the sensor consists of a bent square loop deposited on an aluminum dielectric substrate. So when we increase the temperature from 25 to 1000 degrees Celsius, there is a change in the frequency response for the incident electromagnetic wave. So they come up with some 0.81 megahertz per degree Celsius as the sensitivity of the designed FSS. So this is the FSS they have designed, and that was put to variable temperatures, and if there is any change in the structure, that will be sensed using this horn antenna, because for the incident electromagnetic wave, if there is any change in a structural deformity in the FSS, that can easily be detected using the incident electromagnetic waves response. Okay. So yeah, so this is what for 0, 10, 20 and 30 degree there is a variation. So this is all about the FSS screens, frequency selective surfaces. We discussed about what is FSS and some 5 to 6 applications of FSS. So we are not limiting the application only to these 5 to 6 applications. Maybe there are a number of applications. Again, depends upon our imagination how we are going to make use of this technology. So we dealt with all those applications. What we are going to do with this? So we are going to have the 6G in the future. So from 1G to 5G, the purpose is to build wireless communication and in turn provide a seamless connectivity. And we are also interested in enhancing the bandwidth to realize certain applications like VR and AR. Okay. So apart from that, what may be the reason why we go for 6G apart from bandwidth? Any guesses? So we are more comfortable with this 5G, even though we are not we are comfortable with 4G. We have gone for this 5G in the sense increased bandwidth to provide seamless connectivity and high data rates. So what may be the objective of 6G? So we have a document in the Government of India's website. So that is Bharat Vision 6G statement. So I think it runs some 500 to 600 page. There they have given what is the future with this Bharat Vision 6G statement. So they are going to launch this 6G by 2030. And what is it expected from the organizations of India, academicians, academic organizations and industries from India? Okay. So what may be the objectives of this 6G? So the objectives are is to run without the need of batteries. It is difficult, but still the objective is to run all these devices obviously not without batteries, at least to reduce the battery power consumption. So the target efficiency of 1 picojoule per bit. So all these are extracts from the Bharat Vision 6G document. So aside from the advantage of high power terahertz waves, the 6G communication allows for directed beam communication through MIMO or massive MIMO, which allows device to transmit power beams in a specified direction. So that's what the objective behind this 5G as well, and they want to enhance its performance in 6G. So the two objectives are like, the first one is to reduce the power consumption, next one is to targeted beam steering. And this is again an extract from the article what I have written, the IEEE spectrum. So castles in the sky. So when we speak about this, the need for energy, the need for batteries, need for power, definitely we are all into this solar power, okay, which is the renewable energy. So the countries across the globe are planning to set up this solar castle in the sky. I hope, yeah. So the plan is like, we have thin film reflectors, okay, that will track the sun and concentrate sunlight, okay, onto the earth, which has some receiver, which will in turn convert that signal, okay. So using this microwaves or even millimeter waves or even terahertz wave, we will be able to transmit the power, okay, from the space segments, which has converted the solar energy into electrical energy, and that can be used for the applications or the appliances on the earth. So this is the plan. And next is the windows, like I have touched upon this dual band. When I spoke about this dual band FSS, I touched upon this point. The windows are now getting converted to 5G base stations. This is now active in Japan. One of the company, RJ, I think, yeah, they have come up with this, converting the windows which is used in most of the scrappers as 5G base stations. As when we move from 4G to 5G, we are enhancing the bandwidth, and that will in turn provide seamless connectivity, but at the cost of what? We have path loss. When we move from FR1 to FR2, we make use of high frequency signals, because of which there will be path loss. So if you want to provide again enhanced connectivity, then we need to go for installing more number of base stations. So that can be overcome with the help of this technique, which is being deployed in one of the one of the companies in Japan. So where they have converted the windows, glass windows. So the transparent antenna, okay, the transparent antenna can be engineered, okay, so that it will not it will not affect the electromagnetic signal, okay, and the reflection of the radio signals will be absorbed definitely, but not to an extent what a normal glass is absorbing as well as attenuating, okay. So this is the image what I received it from, again, IEEE spectrum. So there's a deployment of new glass antenna that turns a window into a base station, okay. So that can be attached to the building window, and that will provide the service indoor. So this is the future of antennas. Like we have this transparent antennas nowadays being used. This is one of the best use case, okay. Yeah, so these are some of the applications. Yeah, with this I'll close the session. If you have any doubts, yes.
Thank you, sir. Thank you so much for this insightful presentation. We also extend our gratitude to Anju ma'am for chairing the session. We now open the floor for a short doubt clearing session. If you have any doubt, please feel free to ask.
So I'm curious about some of the applications that I have in mind. So mostly around drones, okay, right? So you mentioned about absorption and reflectance for applications such as blocking jamming signals, yes, or something like that, right? So drones is a particularly beautiful example where we can, because we are seeing in Ukraine, Russia, yes, every day innovation is happening at such a huge pace, right? So what's the size and weight for these things? Because ultimately if you want to deploy it on a drone or something like that, right? So one application that comes to my mind is like the drones can themselves form a periodic array kind of thing, and you can deploy one of these patches on one drone like that.
Yeah, we can go for adaptive kind of.
Yeah, so that is one application.
Yes.
So for an entire array to be deployed on a single drone, what could be the? So you showed some pictures here,
Yes,
right?
yes,
So what's the typical size and weight, like ballpark numbers?
What I have shown is like 30 centimeter cross 30 centimeter, 1 feet cross 1 feet.
Okay.
Yeah, we can. The thing is like if we go for drones, we need to make sure that the unit cells are much closer to each other as well as much smaller. So that's where the angular independency as well as the stability lies in.
And these can be printed on some fabric or some sheet kind
done.
of a thing.
That
So
can be.
the weight can be reduced, right?
Yes, yeah, we have tried ones like just in a white paper. We have pasted some conductive inks and it provided some 15 to 20 dB of attenuation. That is possible.
So keeping it under
Again, the temperature and all those things we have to test.
Okay.
Deployment and also the moisture content, all those things definitely plays a very important role.
Okay.
Yeah, this is interesting application for me as well.
That is one thing. The other is, are these things unidirectional or bidirectional? So let's say
Bidirectional.
if you okay.
Bidirectional. S1 to S1 to
No,
remains.
what I'm getting at is, let's say if you deploy it on a drone, let's say, right, and there is a jammer which is trying to jam the communications of the drone itself, right?
Okay.
But if you put this thing in front of it, you can effectively save the drone, but the drone would not be able to communicate to its ground troops or something like that, right? So if it can be made unidirectional so that you can avoid jamming, but you could still transmit in the other direction, it would be a beautiful application.
Yeah, in that scenario, like what I can suggest, like suppose if the two different frequencies are used, then definitely we can bring in this application.
Okay.
Suppose if jamming is happening on particular frequency, we can stop it.
No, you mentioned 2.4 and 5 gigahertz, both can be suppressed, right?
Yes, yes.
So typically jammers operate at the entire band, sub 6 gigahertz. They would want to block everything.
Okay.
Because military bands are not using ISM bands, right?
Yes.
So that is one thing. The last is, have you heard of the company called Ecodyne? So they make these metamaterial based phased arrays, so to speak.
Okay.
Which are miniature size and basically for communications only, and radars also.
Okay.
Basically, I have no clue how they have implemented it or how metamaterials perform with respect to regular phased array design. Regular phase beam forming and all this, and beam steering and all is there. But how to do it with phased arrays? Have you are you aware of such research, or have you seen something like this?
No, we have designed some phased arrays
with metamaterials. I mean FSS structures.
FSS. But Ecodyne, I don't know what is the concept they are using. Maybe I'll check it. And
I'll get in touch with you on
sure,
that.
Sure, definitely. That is Ecodyne.
Ecodyne. ECHODYNE.
Okay. Yeah. Once we visited some of the industries in Chennai, we came to know that all the 5G stations are making use of this massive MIMO. There they have some metamaterial as well.
Right.
There it is not antenna is not a different entity. Now everything is integrated. Yes. So the feed to that antenna structure, which looks like some 5 centimeter plus 2 centimeter, will have only two wires. One is to power up, another one is to receive signal or to transmit signal. Everything is integrated. So maybe I'll check with that and get back.
There's a huge market for that.
Yes.
If you can bring that to India, Indian Defence Forces especially, phased arrays, replacement for phased arrays, because the chips behind these phased arrays, the beamformer chips, are very expensive and export controlled.
Sure.
So if you can build something which is passive in nature, there is nothing like it.
Yeah. So thank you for those inputs as well.
Sir, while designing FSS, so what are the factors that affect the angular stability?
The height of the substrate, then the distance between the unit cells, and size of the unit cell. These three things you need to take care.
Mainly the size of the unit cell.
Size of the unit cell, the periodicity we call like X and Y distance between the unit cells, and sometimes the height of the substrate also play I cannot have some 3 to 4 layers. Yeah, like it will influence the order in which I have said. First is unit cell and then periodicity. Third one is like the height of the substrate. Yeah.
Thank you, sir.
In connection with that question, how did you measure the angular stability in your measurement setup?
Yeah, so we measured it using two modes, sir. The first one is like we have changed we placed two antennas the first thing is we change the orientation of the antennas, then we measured what is the response of the FSS, and the next thing is like we change the orientation of the FSS again and tested what is the performance of the FSS. So two ways we can measure. We no need to measure the phi, because phi is like you are rotating it in the same axis. So when I want to check the stability of the FSS, either I can change the angular angle of attachment of or axis of this FSS, or I can change the incident angles, electromagnetic source, that is the horn. We can test in both ways, but what I suggest, like we have to change the FSS.
But then you are getting the blazing only. You are using monostatic.
Monostatic, yes sir.
But what I am asking is, to get the angular stability,
Yes.
you need to have a bistatic. You haven't tried that.
No sir, we haven't tried. No, we haven't tried sir. Only monostatic we have tried.
Because if it is going to the other angle,
Yeah.
because even if you put a metal plate, you won't get back reflection at 30 degree or something.
Yeah. So back.
Even if it is a perfect conductor, metal plates.
Okay. So back reflections, like yeah, for absorbers we have tested those back reflections as well, sir. For band stop or band pause, we haven't gone for this reflection measurements. For absorption, we have tested the reflection measurements as well.
Yeah, for phi it is okay. You can
Yes.
do monostatic, but
Yes. Maybe we'll try include that too as well, sir.
thank you.
And for those measurements, we understood that larger the fabricated prototype, better the performance is like. So for the antenna, the illumination area should be like the FSS area should be twice that of the antenna illumination area, so that we got the better performance.
So, before we conclude this session, we would like to take a moment to express our gratitude to our distinguished speaker for sharing their valuable insight with us. We now invite Dr. S. Ramprabhu to kindly accept a token of appreciation as a small gesture of our thanks. I request Anju ma'am to do the honor.